Hi guys, and welcome back to my channel. In this video we're going to be deriving the energy levels for a particle in a box using the one-dimensional Schrödinger equation. So the Schrödinger equation looks like this. The Hamiltonian of the wave function equals the energy of the wave function times the wave function. And the one-dimensional Schrödinger equation that we'll be using looks like this. This is just an expansion of the Hamiltonian, negative h over 8m pi squared times the second derivative of the wave function plus the potential function times the wave function equals the energy of the wave function times the wave function. Okay, so now let's draw out our system, right? We're looking at a particle in a one-dimensional box. So let's draw our one-dimensional box, and let's say that this box has a length L. So we'll call the left point x equals 0 and the right point x equals L. So we want to ensure that this particle is always within the box, right? The particle can never be outside the box because this is a particle in the box. It's confined to the box. So how can we do that? What we can do is we can set the potentials outside the box equal to infinity, and the potential inside the box equal to 0. So what does a potential outside the box of infinity mean? This basically means there's an infinite barrier, right, that the particle needs to overcome in order to leave the box. So it basically means that the particle can never leave the box. And inside the box, we can define this value as anything, but the potential being 0 is really convenient because what happens when we plug 0 into the potential, right, this second term from our Schrödinger equation will be gone, right? We'll sort of get rid of it. So this is why it's really convenient to define the potential inside the box as 0 and the potential outside as infinity. And we need to define the outside potential as infinity because that means that there's an infinite barrier that the particle must overcome to be outside the box, which means that the particle is confined to inside the box. Okay, so now we can simplify our Schrödinger equation to look like negative h over 8m pi squared times the second derivative of the wave function equals our energy times the wave function, because we can eliminate, because our potential is 0. This is a really common form of a differential equation where you see that the second derivative is equal to some multiple of the actual function itself. And when you have a differential equation of this form, what you assume is that the wave function looks like this. Looks like a sine kx plus b cosine kx. Now let's take the second derivative of this specific form of the wave function so I can show you how this will work with this specific differential equation. So if we take the second derivative, right, we'll end up getting that this equals negative k squared a times sine kx minus k squared b times cosine kx. And this also just equals minus k squared times the function itself. So you can see how the second derivative is basically just a multiple of the function itself. Now what we can do is we can plug this equation for the second derivative back into our Schrödinger equation. So I'm going to rewrite this by using that substitution. So we'll get negative h over 8m pi squared times our negative k squared psi equals the energy times psi. And if we divide by psi the wave function on both sides, we can get what our energy term is. So our energy is equal to k squared h divided by 8m pi squared. Okay, cool. So now we're going to look at what are called boundary conditions of this particle in a box, and we're going to see how this sort of reduces the amount of wave functions that are possible. So I'm going to redraw our particle in a box picture. We have our length L, and we have x equals 0, x equals L, our potential as infinite on the two sides, and our potential is 0 in the middle. And we also have our energy term. Energy is k squared h divided by 8m pi squared. Okay, So what do we know about our wave function at x equals 0 and x equals L? The particle must be confined to inside the box. This means that at the boundaries, our wave function must be 0. Because if our wave function is 0, that means our wave function squared is 0. And remember that our wave function squared is the same thing as our probability density function. There shouldn't be any probability that we find our particle at the boundaries of the box, because our particle must be confined to the inside of the box. So basically what this tells us is that our psi at 0 and our psi at L must be equal to 0, right? So let's see what this actually gives us. If we rewrite what our psi function was, it looked like a sine kx plus b cosine kx. If we plug in psi of 0, right? Let's do this, plug this in. We'll get a sine 0 plus b cosine 0. And psi of 0 must be 0. Since cosine is 1, cosine 0 is 1, so this term becomes 1, this term becomes 0, so you'll end up getting b equals 0. So basically our cosine term is eliminated. Now we have that psi equals a sine kx. So how can we get that psi of L now also equals 0? What we can do is we can take k as equal to n pi divided by L. And I'll show you why this works. So let's plug this in and we'll look at the boundary conditions. Psi equals a sine n pi x over L. If we take psi of L, right, what does this give us? This gives us a sine, our x will become an L, the L over L will cancel, and this will just become n pi. As long as n is an integer, when n is any integer, 1, 2, 3, etc., n times pi is going to give us some multiple of pi, and the sine of a multiple of pi equals 0. So this will end up equaling 0, and that's what we want. We also want to note that n cannot equal 0. If n equals 0, right, then our psi will equal 0 for all x. And that doesn't make any sense, because that means that there's no probability that the particle is in the box at all, which means that the particle is not in the box. So note that our n must be a positive integer, 1, 2, 3, etc. Okay, so now we've sort of got our form for our psi. Let's now look at what the energy is, right? We've got that k equals n pi over L. So we can now plug our k expression in and figure out what our energy is. So our energy, right, equals k squared h over 8m pi squared. If we plug in that k, we get n pi over L squared times h over 8m pi squared. And if you simplify this, you'll end up getting that the energy is n squared h squared over 8ml squared. And this is a really, really important expression that you probably will want to sort of have in your brain, because you don't want to keep deriving this whenever you see a particle in the box problem. And in this video, we'll sort of go over a really cool example of a particle in a box problem. So now let's look at our psi, right? How do we figure out what our A term is in our psi? That's what we're going to do in the next slide. So psi equals A sine n pi x over L. But we know that psi squared is a probability density function, right? And with probabilities, when we sum up all the probabilities over the entire space that the particle can be, we must get 1. So that's sort of another condition that we can use in order to determine A. So psi squared is a probability density function. So what this means is that if we sum up over the entire place where the particle can be, which is in the box, and the box, remember, is from x equals 0 to x equals L, and we integrate psi squared, we want to set this equal to 1. And this is our condition. So if we plug this in, you would get 0 to L, you can a squared sine squared n pi x over L, and take this integral and set it equal to 1. And if you do this, you'll get that a equals 2 over L to the power of 1/2. So our entire psi function, our wave functions, would look like 2 over L to the power of 1/2 times sine n pi x over L. So these are the two key expressions you want to have in mind. You want to know what your wave functions look like, and you also want to know this energy expression, especially the energy expression. It's really, really useful, and we're going to go over a problem that utilizes this equation in a pretty cool way. Okay, so for this problem, we're going to be looking at the molecule beta-carotene. And if you don't already know, this is the molecule in carrots, and it gives the carrots its orange color. So this molecule is orange. So now we're going to justify why beta-carotene is orange using our knowledge from the particle in the box. So how does this molecule have anything to do with particle in a box, right? First, you can see that there's this really long conjugated pi system for beta-carotene. There's a bunch of double bonds that are conjugated with each other. And each of these double bonds has pi electrons, right? And these pi electrons are sort of delocalized across the entire conjugated pi system. But these electrons also cannot exit the conjugated pi system. They can only stay within this sort of conjugated pi system. So this sounds a lot like particle in a box. The electrons can only be found, the particles can only be found within this certain region, and they cannot be found outside this certain region. So let's sort of model this molecule as particles in a box. And we can treat this molecule as a one-dimensional box with a length of 1790 picometers. Okay, so we can also see that in this molecule, if you count the number of double bonds, we have 11 double bonds. And this means that there's 22 pi electrons that are delocalized. And free to move around this quote-unquote one-dimensional box. We also know that the energy levels that these electrons can fill are given by n squared h squared over 8 ml squared. So if we sketch an energy diagram, right, and we start out with n equals 1, n equals 2, we'll end at n equals 11, because each of these orbitals, each of these molecular orbitals, can hold 2 electrons, and we have 22 pi electrons in total. So we'll have all of these orbitals occupied up to n equals 11, and the n equal 12 will not be occupied. So what happens when light hits this molecule, right? When light hits this molecule, this gives an electron in the n equals 11 orbital enough energy to jump up to the n equals 12 orbital. This is exactly like Planck, right? What we talked about, where the difference in energy will be proportional to the frequency. And some frequency is going to be absorbed, and that's going to jump up to the n equals 12. So this is what we call the HOMO, the highest occupied molecular orbital, and this is what we call the LUMO, the lowest unoccupied molecular orbital. And when light shines, there's a certain frequency is going to be absorbed, and an electron from the HOMO will jump up to the LUMO. So basically what we want to find is the energy difference between the HOMO and the LUMO, and see what frequency that corresponds to. So let's do that, right? So the delta in energy is going to be, if we plug in n equals 12 and n equals 11, we'll get 12 squared h squared divided by 8 ml squared minus 11 squared h squared over 8 ml squared. And this gets you 23 h squared over 8 ml squared. Okay, and if we want the frequency now, right, remember that frequency, the delta energy, is equal to Planck's constant times your frequency. So we just needed to divide by Planck's constant to figure out what the frequency absorbed will be. The frequency absorbed will be 23h, not squared because now we're dividing by Planck's constant, divided by 8 ml squared. And if we plug in our length as 1790 picometers, we plug in our mass of the electron, and we plug in Planck's constant, what we'll get is that this frequency is 6.526 times 10 to the 14 hertz. And if you convert this to wavelength using the fact that the speed of light is the wavelength times the frequency, we get that the wavelength is 459 nanometers. And now you might be saying, this looks like kind of like a low wavelength, right? This would probably be more on the bluer end of the spectrum. How can that be? Isn't the molecule supposed to be orange, right? But remember that this is the wavelength that is being absorbed, which means that what you actually see is the reflected wavelength, which is the complementary color. And the complementary color of this wavelength is actually orange. So complementary color is orange. So this was I thought was a really cool example, and just being able to show that beta carotene is actually an orange molecule using pretty simple energy level ideas is pretty powerful. I hope you enjoyed this video, and thank you so much for watching. I'll see you in the next one.